So just want to thank you all, first of all, for choosing our planetarium this evening. I know you have a lot of fun things you could be doing. And
This is fun.
I'm so glad to hear that. And tonight we're going to have a particularly nice presentation on solar eclipses. We have Dr. Jeff Rich with us, who did his undergrad actually locally at USC, and is now with Carnegie Observatory. So join me in welcoming Dr.
Thank you, Barbara. Thank you so much for having me. So I'm here to talk about eclipses, but I always start every talk locally by asking everyone, how many of you have heard of Carnegie Observatories? Okay, that's not bad. For those of you who haven't, that's the place where I work. I'm an astronomer. It's a research institute in Pasadena. We've been around a really long time, but we're really well hidden and we're not that big. We have an open house every October. We haven't set the date yet, otherwise I'd be telling you to come to our open house in October. It's going to be the second Sunday in October, very likely. We are in Pasadena because of the two gentlemen in that picture, George Ellery Hale, who is a solar physicist from Chicago, and Andrew Carnegie, who is incredibly wealthy and gave his money away to a bunch of endeavors, including endowing the Carnegie Institution of Washington to fund science. George Ellery Hale convinced Andrew Carnegie that we should build telescopes here in Southern California because it was 1904 and there was no light pollution yet. But Mount Wilson Observatory was our original observatory. It's still there. The telescopes are still great. Many very important discoveries were made at Mount Wilson, which I won't be talking too much about tonight, including discoveries about the sun. You should go visit Mount Wilson if you haven't. It's really spectacular, but those are our original telescopes. Because of light pollution and for a few other reasons, we built telescopes elsewhere. So again, offices are still in Pasadena. That's where we work day to day. But our modern telescopes, the astronomers that work at Carnegie use telescopes in Chile, in the Atacama Desert, where it's much, much darker, and you can see a whole different part of the sky. We are a relatively small place, but we have a machine shop, we have engineers, we have folks who build instruments, we have theoretical astrophysicists who use computers to model the universe. So again, I wish I'd set the date for our open house and I would advertise it to you right now, but I'll have information at the end if you want to sign up and get more, if you want to hear about our open house.
You have a website?
We do, and I'm going to plug it at the end, and I have postcards down here with that info. And that's all I'm going to say about Carnegie for now, because I came to talk about eclipses.
Just back to chairs. I don't want to scare anybody. Your chairs will go back. I'm just realizing we're kind of all afraid of our chairs.
Well, it's good timing anyway, because now I'm actually going to talk about eclipses. So I thought it would be fun to talk about eclipses because we just had a major eclipse in North America. Eclipses won't be stopping. There are some more coming up. And just so we're all starting at the same baseline, as a reminder, there are two kinds of eclipses that we see here on Earth, solar eclipses and lunar eclipses. The solar eclipse happens when the moon blocks the sun and casts a shadow. A lunar eclipse happens when the Earth blocks the sun and blocks the light hitting the moon. To get even more basic, I want to just start you off on the most basic level and say, this is all, we're talking about eclipses in the solar system. The solar system is the sun and everything that goes around it. The thing that causes eclipses is the motion of the Earth around the sun and the moon around the Earth. As a reminder, my video working? Yes, okay. The Earth is constantly rotating on its axis. One rotation is 1 day, and the Earth is going around the sun. One trip around the sun is 1 year. And as that's happening, the moon is also going around the Earth. So this is a nice little animation from NASA that shows sunlight is always coming from the same direction, so it's simulating what side of the moon is lit up and what side of the Earth is lit up, and the way that the moon looks from the Earth will change depending on the alignment of the Earth, the moon, and the sun. This is what gives us phases. This is why you get a new moon, a first quarter moon, full moon, third quarter moon. It depends on where you are, where the moon is with respect to the sun, where you are on Earth while you're looking at it. Just a reminder, these are those alignments. If the moon is in between the Earth and the sun, that's a new moon. You're seeing the nighttime side of the moon. Opposite that is a full moon, when the moon is on the opposite side of the Earth from the sun. So you're seeing the entire daytime side of the moon, and everything in between. So I said eclipses happen when the moon is blocking the sun or the Earth is blocking the sun. That happens when everything lines up. So you can get a solar eclipse at new moon, when the moon is in between the Earth and the sun. And you can get a lunar eclipse at full moon, when the Earth is in between the moon and the sun. Okay. This is another illustration of that. On the bottom is how the moon looks from Earth during that time period. Full moon, obviously, opposite side, new moon, in between. Okay, I'm gonna hammer that point home. So coming back to eclipses, that's when everything lines up. Everything lines up. There's a full moon about once every 28 days, and there's a new moon about once every 28 days. So are there eclipses once every 28 days? Is there a lunar eclipse this month?
No.
Again, you might not know, but there is not a lunar eclipse this month, just so you know. So why isn't there an eclipse if everything lines up? If there's a full moon every 28 days, and then a new moon 14 days later, and then a full moon 14 days later, why is there not a solar eclipse every new moon and a lunar eclipse every full moon? Does anybody happen to know the answer? Because there just wasn't an eclipse, you might have learned about this already. Anyway.
Different plane. The plane of the ecliptic and the plane of the moon's rotation are different.
The moon's orbit is slightly tilted with respect to the ecliptic, the sun's or the Earth's orbit around the sun. So this is an illustration of that. I have a cute little video that shows it. Excellent. So this would be like a top-down view of the moon going around the Earth. And the shadows of the Earth and the moon are shown here. And if you remember, we live in a three-dimensional space. Everything has to line up just right. Most of the time, most full moons and most new moons, there is not an eclipse. So there's solar eclipse, no solar eclipse. If things line up just right, the moon's shadow will be cast on the Earth's surface and you end up with a solar eclipse. So that's what happened in April of this year across North America. The other thing is sometimes things are almost lined up but not quite. So you can have a partial eclipse rather than a total eclipse. This is the same for lunar eclipses as it is for solar eclipses. On the top is a sequence of images of the moon passing in front of the sun. And on the bottom is a sequence of images of the Earth's shadow being cast on the moon. Anything that's not total is partial. Makes sense, right? Statistically, I'm an astronomer, so we use really big error bars. I'd say about a quarter of eclipses are total. It's a little bit more. 27% of solar eclipses are total eclipses. About a third, about 30% of lunar eclipses are total lunar eclipses. So most of the time, if there's an eclipse, it's not a total eclipse. One thing about lunar eclipses is it's much easier to have a total lunar eclipse than it is to have a total solar eclipse. And a total lunar eclipse can be seen anywhere you can see the full moon. And the nice thing is the moon is not as bright as the sun, so you can look at the moon anytime you want to. There's no lunar eclipse glasses. The next total lunar eclipse that you'll be able to see from North America is actually next year. And during totality, a little bit of sunlight passes through the Earth's atmosphere and is cast onto you end up with a little bit of red light making it to the moon's surface. So the moon doesn't get completely dark like the sun does. It actually looks a little bit reddish. You might hear this called a blood moon. It's just a fancy way of saying the moon looks a little bit red when it's completely obscured in the Earth's shadow. I put the dates here just so you all know. There is actually a lunar eclipse in September, but you will have to strain your eyes to see it because most of the time the moon will be in the Earth's penumbra, which is a part of the shadow that's really not, you basically won't be able to see it. You won't be able to tell any difference from the naked eye. For a tiny fraction of time, it will pass through the Earth's umbra, and you'll see a tiny bit of moon missing if conditions are just right at 7:44 p.m. So I would not hold my breath for this eclipse. I just wanted to put it here for completeness sake. The next total lunar eclipse that we'll be able to see is next March. The trick is it doesn't get completely blocked until about midnight. So you'll have to stay up late if you want to see that really dark red moon. That's really, that's not too late. You don't have to wake up at 3 a.m. But even by 9 o'clock, the eclipse will begin. You'll start to see the moon get blocked a little bit. It takes a while. I'm going to show that with the planetarium later. A lunar eclipse is not something that you'll want to sit all night and just stare at the moon. You can take a look outside, go back to doing something else. Maybe you can go to sleep, set an alarm, wake up, go back and check at midnight. But this is the next lunar eclipse you'll be able to see from here. And the entire continent, basically the entire part of our hemisphere will be able to see it. Anywhere you can see the full moon during that time, you'll be able to see the lunar eclipse, which is very different than the solar eclipse, as you all probably know. I added this as a demonstration. So this is a side view schematic of how everything lines up during a lunar eclipse. The outer part of the shadow is called the penumbra, the inner part is the umbra. The umbra is the part that actually looks like you're seeing the Earth's shadow obscuring the moon's surface. The one in September is basically the moon spends most of its time in the penumbra. You probably won't notice anything. Don't worry about that one. You'll see a partial and total eclipse once it moves into that umbra. So everybody mark your calendars, March 13th. Check out the eclipse. Solar eclipses, way more spectacular than lunar eclipses. I don't want to ding lunar eclipses, they're very fun. But there was just a total solar eclipse this year in April. How many of you looked at the eclipse on April 8th? How many of you viewed the eclipse somewhere? How many of you viewed it in the path of totality, like the actual total loop, so the sun was completely obscured? So did you all see it from here with eclipse glasses, or you saw shadows? Excellent. So you all, most of you saw something, so you know an eclipse happened. So before we get into it, I wanted to just mention that we're in a really lucky spot to see eclipses. Not lucky, it's just a coincidence for now that even though the sun is much bigger than the moon, about 400 times bigger than the moon, it's also about 400 times further away from us than the moon. So as a consequence, the Earth and the moon the sun and the moon are about the same size in the sky, about, roughly. So that means if everything lines up just right, you can get the moon completely covering the sun. I mentioned that doesn't happen very often. Most eclipses are partial eclipses, and occasionally the moon doesn't completely block the sun, and that's called an annular eclipse, and I'll come back to why that is. And the other really important thing about solar eclipses, as all of you who watch the solar eclipse here know, it's very different than a lunar eclipse. The moon's shadow is only cast on a narrow strip on the Earth's surface. So you can't see a total solar eclipse everywhere that you can see the moon on the day of a total solar eclipse. A lunar eclipse, totally different. A total lunar eclipse is totally different. You can see those anywhere you can see the moon that day. The total solar eclipse, you had to be in certain spots on the Earth's surface to see that the moon completely block the sun. There are lots of different ways of showing it, but basically this is another diagram. You can see that little circle is a projection of the moon's shadow on the Earth's surface. That shadow varies in size depending on the Earth, Sun, Moon distance from each other. Typically the shadow is this circle about 60 to 70 miles across. It can be much wider, it can be much smaller, it can be non-existent. Depending on how big the shadow is and how things are lined up, the amount of time the moon spends in front of the sun can be quite long. It can be up to 6 or 7 minutes. Typically it's much shorter, 2 or 3 minutes total, when the moon is blocking the sun entirely. If you want to see a total solar eclipse and you don't want to have to leave wherever you are, you don't want to have to leave where we are right now, you'll have to wait a while. On average, any one spot, like if we're standing here and we average out everywhere across the Earth's surface, any one spot sees a total solar eclipse about every 375 years. I have the dates for Dallas in here because that's where I was for the total solar eclipse this year. So we were telling everyone in Dallas, please go outside and watch the eclipse because the last time was in 1878 and the next one won't be until 2317. Unfortunately, in Los Angeles, I was trying to look this up before the talk. So the last one in Los Angeles area was in 1724. And in the available atlas of eclipses on the NASA website that I used to look this up, there were no eclipses visible from Southern California until after the year 3000, and the atlas only goes until the year 3000. So if you want to see a total solar eclipse, unfortunately you'll have to get out of Southern California, but we'll see lots of partial eclipses. This is another way of illustrating that. So I said on average any one spot is every 375 years. This was a graphic made by the Washington Post in 2017 for that eclipse. The darker the area, the more eclipses that particular spot in the United States has seen. The brighter since 2000, the lighter the less eclipses. So it's not guaranteed that you'll get one every 375 years. That's just on average. And what is it? Past performance is no guarantee of future success. There are about 2 solar eclipses every year, but only about 1 out of every 4 of those is a total solar eclipse. The reason for this variation in the size of the shadow, the reason for is not just because of getting things to line up just right because of orbits, it's also because the moon and sun, mainly the moon, actually look a little bit bigger or a little bit smaller depending on where the moon is in its orbit and depending on where the Earth is in its orbit. The sun changes in size in the sky, it's not actually getting bigger and smaller, just because we're in an elliptical orbit around the sun. It changes by about 3%. The moon changes a lot more, and this is because the moon is in an elliptical orbit and the Earth is in an elliptical orbit. So sometimes the Earth is a little farther from the sun. We call that aphelion. Sometimes the Earth is a little bit closer to the sun. We call the closest approach perihelion. And this is a time when we always like to remind you that the distance from the sun is not what causes the seasons. The dates are on here as a reminder. So the Earth is actually closest to the sun on or about January 3rd, when it's winter in the northern hemisphere. So you'll remember the seasons are caused by the fact that the Earth is tilted. So around that time of year, the northern hemisphere is tilted further away from the sun. We get a different amount of sunlight. Anyway, that's just a reminder. So distance from the sun changes. You'll all remember that, but that's not what causes the seasons. This is a side-by-side comparison of how much the sun's size changes from perihelion to aphelion. This is not what dominates the change in the solar eclipses. It matters. You have to math it out, but it doesn't matter as much as the moon. It does matter more if you're on other planets. I like this website that I found these images at. Different planets have different orbits. They're at different distances from the sun. And Mercury, for instance, is much closer on a much more elliptical orbit, or the percent change is much larger. So Mercury's closest to the sun appears much bigger in the sky. Same for Mars. The Martian orbit is more elliptical than Earth's, so the size of the sun is changing more than it does for us. I can't see Neptune, so don't worry about that. The moon, in part because it's much closer, is changing its apparent size in the sky much more as it goes around the Earth. So this is really what dominates the ability to have a total solar eclipse and whether that eclipse will be long or whether it will be short. So there can be a situation where the moon is a little bit too far away from the Earth and the sun is a little bit bigger in the sky than the moon, but everything lines up just right. You have the sun and the moon moves in front of the sun, but the moon is too small to completely block the sun. Then you have an annulus, a ring of light left around the moon's edge, and you don't get a total eclipse. This is called an annular eclipse. One of these actually crossed the United States specifically, last October 2023. I did not get a chance, I have never seen one of these where the moon is completely in front of the sun but just a little too small to block the sun. But that's what it looks like. And just a note, this eclipse is not unique to Earth. They can happen anywhere where you've got the right alignment of moon, planet, and sun. Eclipses happen elsewhere in the solar system, on Earth, Mars, and on all 4 giant planets. You might remember Mercury and Venus don't have any moons, so unfortunately no eclipses for them. And you might also know that Mars's moons are much smaller than the Earth's. So even though Mars is much further from us than the Sun, which means the Sun will appear smaller in the sky, and even though the Martian moons are closer to the surface, they still aren't big enough to completely block the Sun. So all of the eclipses on Mars are annular eclipses or partial. And this picture is an actual picture of a solar eclipse taken by a rover on Mars, where it was on the right spot on Mars for everything to line up just right to see, oh man, is it Phobos or Deimos? Only one of them can actually eclipse the Sun. Don't quiz me on that, I'll have to look it up. And just to get super technical, because we're in a planetarium, eclipses are also transits or occultations. So if something is passing in front of another object, we call that a transit. So every now and then the planets Mercury or Venus will pass in front of the Sun, and we call that a transit. This happened in 2012 for Venus. Those little circles are the planet Venus moving in front of the Sun. It's not really eclipsing the Sun, but it is. It's a trick of language. And if something passes behind another object, we call that in astronomy an occultations. The picture on the bottom is a picture taken at Mount Wilson of the moon occulting Mars. Mars is just creeping out from behind the moon's edge there. That's your technical terms for the night. The other thing that you need to know is that we eventually here on Earth won't have total eclipses anymore. The moon is slowly increasing its distance from the Earth, about 1 inch a year. And the Sun is very slightly increasing in size. And so in about 650 million years, the moon will be so big in the sky and the Sun will be so big in the sky and the moon will be so far from us that there will be no more total eclipses. You've got time. I wanted to just talk briefly about who got to see the eclipse in 2024. So the great thing is everybody in North America got to see at least some kind of eclipse, partial or total. To see the moon completely block the Sun, you had to be in that yellow strip called the path of totality. The width of that strip depends on how big the moon's shadow is on the Earth's surface. This year it was a little bit bigger than average, so the length of totality, it changes along that path, but it was about 4 minutes and change. And the moon is moving through the sky as it's orbiting the Earth. The moon's shadow is being cast on the Earth's surface from west to east. So if you imagine, I have a video that actually shows this, the moon's shadow moved across the continent. It started in Mexico and then basically crossed Mexico, the United States, and Canada and flew out over the Atlantic Ocean. And if you happen to be anywhere inside that circle, then the moon will completely block the Sun for at least some period of time. What's interesting is it depends on where you are in that shadow. So if you're right at the edge, the moon will only block the Sun for maybe even a few seconds. If you're right in the middle, it would be much longer. The really unique thing about this eclipse is it passed over a lot of really big cities. So there were, just in the United States, over 30 million people who all they had to do was go poke their head outside and cross their fingers that it wasn't cloudy. And so a lot of people got to see this total solar eclipse without having to go anywhere. And everybody in the country got a chance to see an eclipse if they had the chance to step outside and put on some eclipse glasses. And I brought some eclipse glasses tonight, and I'll explain why at the end. We've almost made it to Canada. Okay, there we are. The other interesting thing that I learned that I didn't think about until I watched this video is that the speed of the moon's shadow gets faster and faster as you reach the end of the eclipse path, just because of how things line up. So it's moving across the Earth's surface in excess of 3,000 and 4,000 and 5,000 miles an hour, and then it jets out over Newfoundland. You can also you don't have to be on land. You can hop in a boat or in an airplane and chase the eclipse too if you have the means. So I wanted to talk a little bit about, before I talk about the science, the history and some more science, I thought it would be fun to simulate the eclipse with the planetarium. I was trying to think, like, what could we do with the planetarium? So we're gonna take a break from the talk for a second and show you what it looks like to view an eclipse, since this planetarium can simulate that experience. So this is what the total lunar eclipse will look like next March. This is moving much faster than real time. So right around, I believe totality was at 11:50. It was just before midnight, our time. So the moon will look a little bit red. It looks pretty cool. If you get a chance, and it's not, I can't control the weather yet. So I can't guarantee we'll have good weather in March, but if it happens to be nice weather, it's worth taking a look outside, because lunar eclipses are pretty cool.
Dr. Rich?
Yes?
Is the red refracting around the Earth, and that's how it gets there? Like, how does the light get, if it's eclipse, how does that light actually bend around there? What's happening?
It's because we have an atmosphere, so some of the light is getting, it's getting basically bent by the Earth's atmosphere, and preferentially red light is getting through. It's not really noticeable until the moon is completely covered in totality. Prior to that, the shadow looks more just black because the lit part of the moon looks so bright in contrast. So it's really noticeable during totality. Right, which for a solar eclipse, we don't get that effect since the moon doesn't have an atmosphere. So that's the lunar eclipse. You're all going to see that next March, right? I hope, maybe. So the other thing I wanted to show, or I asked if we could show with the planetarium, is what the solar eclipse looked like, and why we don't, how things line up when there's not a solar eclipse. And so I asked if we could see the eclipse from Dallas, because that's where I was, so I knew the timing and coordinates. So we've all been transported to Dallas, right?
Oh, hold on.
We're
about to get
Dallas.
transported.
Perfect. So we've left Glendale. This is much quicker than the 2.5-hour flight. We made it. It's a little cloudy, but that's okay. So there's the sun. And you'll get a chance to see how everything lines up just right during the total eclipse. So here in Glendale, or anywhere in Southern California, the moon blocks part of the sun. So you would have seen something like this if you had eclipse glasses on. The closer you get to the path of totality, the more of the sun gets blocked. And if you happen to be in just the right spot, everything lines up and you lose the sun for just a little while. Which, if I had no idea what was going on, would probably be pretty terrifying. But this requires an alignment of everything, and you have to be in just the right spot. And so you don't get that, like I said, every month. And so I also asked, did we show what that looks like if you're just cruising along new moon to new moon? And they did something really cool to show that with the planetarium, which I did not see until today. So this is showing the new moon in Dallas again, so same spot. The new moon before the eclipse, that would have been March. The new moon during eclipse, and then the new moon after the eclipse. So the moon is moving around the sky as it orbits the Earth. And this is showing you the path of the moon in the sky. There's the moon. And then, hey, perfect. Okay, what about next month? Give it 28 days and we'll find out. Moon. Moon's getting, there's first quarter, moon's getting more and more full. Okay, we're almost there. The moon will come back around. The new moon is that precise moment when it's exactly at the spot between the Earth and the Sun, but it's not gonna make it. I just thought that was fun to see. So that's why we don't get eclipses ever. I mean, I don't know if it would be better or worse if we had eclipses every single month, though. I guess they wouldn't be as special or spectacular, but it'd be pretty cool. So that's all how eclipses happen. I wanted to talk a little bit about some of the history of how we got to knowing how eclipses happen, so you don't have to be scared when the sun goes dark, and how we actually know when they're going to happen. So there are a couple of websites if you want to go explore yourself when eclipses happen and where eclipses happen, where you can be to see one. People figured this out a while ago. There's lots of evidence in the archaeological record that people sorted out this thing called the Saros cycle, which dictates when eclipses happen. You can go read all about it. I put the name there, so if you hadn't heard that before and you'd like to read more about how to predict eclipses, these are cycles that sort of tell you when you can expect another eclipse to happen. And because of that, people have been doing pretty good at predicting eclipses for a while, but the big problem with solar eclipses is that they might have predicted when an eclipse should happen, but they didn't know where they needed to be. So there were accurate predictions of timing of eclipses before we could predict exactly where the shadow would fall. That had some rough consequences a couple of times. A couple of astronomers failed to predict an eclipse. It's a much bigger job risk in the past. You are in charge of keeping track of time and predicting things. We're better at it now. The first actual prediction of the timing and place of an eclipse that we know of was by Edmund Halley in 1715. So since then, we've been able to predict, okay, if you want to see a total solar eclipse, you need to be in this spot at this time. And so even though there's no atmosphere on the moon is not a flat sphere, it has mountains, and as it's blocking the sun, there's an effect called Bailey's beads, which was described by a person named Bailey, where sunlight sneaks through the ridges and mountains on the edge of the moon's surface during an eclipse and makes this pretty effect that people who've tried to photograph eclipses try to catch. Speaking of that, photography is really how we study the universe now. I love looking at the night sky through a telescope with just my eyes, but taking photos, way better. The first photo of an eclipse was in 1851. And one of the big discoveries that was made using a total solar eclipse was the element helium. It was discovered in light during an eclipse. This weird feature that's caused by helium. That we discovered it on Earth later to confirm, yes, helium is a real thing. So that's where the name helium comes from, Greek god Helios. And that's your trivia for the day. We're still studying eclipses because it's the best time to look at the corona, the outer atmosphere of the sun. And you might have heard about sunspots recently because the sun is very active. So we've been watching the sun and counting things like sunspots, which track how active the sun is. And the outermost part of the sun is essentially invisible when the sun is up because it's incredibly faint. So the best time to see that outer atmosphere called the corona is during a total solar eclipse. The weird thing about the corona is it's a lot hotter than the surface of the sun, and we're still sorting out how you transport energy from the surface to the corona in a way that heats it up so much hotter. So it's a good time to study the coronas during an eclipse. We think there's a connection between the activity on the surface and the corona. You can see this during eclipses, and I'll get you there. So sunspots are regions, active regions on the sun associated with magnetic activity. They're darker because they're a little bit cooler, which was a discovery made at Mount Wilson. Full circle. We've been counting how many sunspots there are on the sun's surface and discovered that there's a cycle where they peak in number every 11 years. So the sun is much more active and then much less active on an 11-year cycle. This is something we've known about for quite a while. What's interesting is if you take a picture of the corona during a total solar eclipse, it will look different when the sun is very active. So this year, one of these pictures is from this year. It's the one in the middle. Okay, good. The sun is quite active right now. The sun's corona looks a little bit more round. When the sun is not as active, the corona looks more extended and extended. So that's pointing to some connection between the activity on the surface and the nature of the corona. Just
Dr. Rich?
Yep.
Sorry, when you say active, what do you mean when you say the sun is active?
One way of, so the sun goes through periods of activity where it's essentially having lots of flares, it's throwing off lots of energetic particles, the amount of the solar wind, the constant flow of stuff from the sun goes up, and that's traced by sunspots, which are showing you the magnetic fields getting wound up. You basically get a lot more stuff coming off of the sun's surface when it's very active. When it's less active, it's much calmer. The solar wind is much more constant. It's sort of if you have flares, they're much smaller. So that's the difference between less active and more active, just in general. And before we're done, I got to mention one more big discovery that was made using total solar eclipses, and that's a proof of Einstein's theory of general relativity. So the really cool thing is, this all happened over 100 years ago, and one of the big predictions when Einstein was figuring out general relativity is that gravity can bend light. And if you're a really big thing like a star, like the sun, you will bend light more. So this is a prediction, and we like to test predictions of theories. So Einstein wrote to George Ellery Hale here in Pasadena and said, how would we observe this? Like, you're an observer, I'm not an observer, I don't know how to look at things using telescopes, but I have this prediction. How would you actually measure light from a star being bent by the sun? Turns out the first attempt to do this that was successful was during an eclipse. Because can you see stars during the day that are not the sun? Really tough. If you want to see a star, your best bet is to wait for a total solar eclipse. Sky gets dark and you can actually see stars. So if you can predict what stars you should be able to see during a total solar eclipse, and you can predict where they should be in the sky, because you're really good at measuring things, you can see if there's any deflection, if they've moved in the sky from where they should be. So someone named Eddington did this. They sent an expedition to 2 different spots on the Earth's surface in the path of a total solar eclipse in 1919, and they measured a slight deviation of a star being bent by the sun. This was a big discovery at the time. I forgot to include the newspaper headline. It's like, heavens all askew. Scientists agog. The same kind of headlines you get when there's a big scientific discovery now. Not baffled. So this was one of the biggest scientific discoveries made using a total solar eclipse. Like I mentioned, eclipses are still a good time to study the corona. This is a picture from a recent total solar eclipse. This is the 2017 total solar eclipse. They had time to study the data that they got and publish it and see what they saw. The different colors are different elements in the solar corona. So it's a time when they go and track and see what information can we get that we couldn't get during an eclipse, and how can we use that to try to understand the nature of the sun as an active star nearby. This year they took the same kind of data, and they also did some other experiments, but it's only been a month, so I didn't see any results yet. I just wanted to mention, when you all saw the eclipse here, you saw something in between these 2 images, and you might have seen shadows looking a little bit different. This is actually an effect that you see during an eclipse. And just a reminder, like I said, I brought eclipse glasses. There's no total solar eclipse coming anytime soon, but whenever we talk about eclipses, we always just like to remind everyone, please don't look at the sun. You're not going outside and looking at the sun day to day. So whether the sun looks like any of these, if there's any sunlight visible, you shouldn't be looking at the sun without eclipse glasses. And the Other thing I wanted to mention is if you want to go see a total solar eclipse, these are the upcoming total solar eclipses up through 2030. Your next total solar eclipse is August 2026. It's visible from Spain, Iceland, and Greenland. So take your pick. In 2027, an eclipse crosses northern Africa, and it will actually go over Egypt, across Luxor, so really cool archaeological places. And I think the next one after that is in Australia, and then China. So you've got lots of choices. And one last thing, you might have seen the news that the sun is very active, and a lot of lucky people got to see aurora about a week ago. When I mentioned that the sun is active, these are pictures of a really big group of sunspots that are happening right now. So the picture on the left is a prominence from that big sunspot group. So the sun is also rotating, right? It's spinning, so those spots are changing where they are in the sky. And the picture on the right is an image from Mount Wilson, where every day that's clear, an observer projects an image of the sun and draws all of the spots on the surface and measures their magnetic field strengths. And this picture is really special because it shows a few things. The current group of sunspots is on the left. That's a bunch of dark regions that correspond to the sun being super active. So all of the flares that have caused the aurora came from that region. The other thing on the on the right, that's a picture of the largest recorded sunspot group ever seen at Mount Wilson, 1947. 47. So it's just showing you the last time the sun was this active, we had a similar sized group of spots. That's just pointing to a lot of activity. And for reference, the big marble there is about the size of Jupiter. And the little marble to the left, the little blue thing, that's the size of the Earth compared to the size of these spots on the sun's surface. So this is it's big. And the reason I brought the eclipse glasses is it's big enough that when the spots are visible, if you put on a pair of eclipse glasses and look at the sun, you can actually see the spots without a telescope. You just put the glasses on. If you have a pair left over from the eclipse, check it out. If you don't have a pair left over, grab a pair and take them with you. And when it's clear, take a look at the sun and just see if you can see any spots.
Patrick?
Yep.
How long is this period of sunspots occurring supposed to last for?
I don't know. It depends on, it can go away in the next week, or it could persist, or it could get bigger.
Just don't know.
Don't know, yeah.
Yeah, I noticed that we're not right now at the peak of that 11-year cycle or anything like that, right?
Right, we're close to it.
We are. Okay.
Yeah. And the strengths of those peaks vary, and that's something we're still studying. 11 years ago, when it's near a maximum in activity, it's called the very creative name of solar maximum versus solar minimum. The last maximum was not as active as this maximum is, or the one before that. So we're still learning how to predict things, which is to say we can't really predict overall activity. We've got some ideas of average, and we have ideas when we observe a flare that are getting better and better at modeling and predicting how much of that will impact, say, Earth's atmosphere, satellites. But I'm not a solar physicist, so I'm a little bit less well-versed in that. I'm going to stop there because y'all are asking good questions. I'm going to throw up this info. I mentioned Carnegie. That's our social medias and website. I brought some postcards that also have that information on the back, so you don't have to take a picture or remember. The QR code takes you to a website to sign up for our mailing list. And thank you all for listening to me talk about eclipses. If you have any questions, I'm happy to answer them to the best of my ability. I study galaxies. Thank you.